Hey everyone, welcome back to the channel. I am your physics buddy. Up until now, we have taken the resistance of a conductor for granted. But have you ever wondered what actually makes one wire different from another? Welcome to the lecture 5 of unit 11. Today we are striping it back to the basics. We are discussing the resistance of conductor in detail, looking at resistivity, length, cross-section area to see how the physical build of a component dictates the flow of charge. We'll also explore some advanced cases of resistance in complex circuits, combination that you won't find in average textbooks. If you haven't seen a previous masterclass on solving mixed circuits, make sure to check out lecture 4 to see these resistors in action. It's time to understand the physics behind the components. Let's get into the resistivity formula.
All right then. So basically in today's session we have to discuss few more properties about conductor. So in the previous classes we talked about conductors in detail and we have to keep all those points in mind to describe amazing phenomena which is shown by a specific type of matter which is supposed to be known as conductor. So conductors are those matter which have capability of conducting charge, or you can say which have capability of conducting current. So how this current is being conducted, we already discussed about it. Or we can say how this charge is being flown. We already discussed about it as the conductors has free electrons in it. So those free electrons are the reason for the conduction. So what we observe here is that suppose if we have a conductor and we just assume this is a conductor, it has some specific length and some specific dimensions and it is connected to a battery of some potential V. It is that same potential which we studied in the previous classes. So what we'll observe here is that whatever current is being flown in the circuit is somewhat which is directly proportional to the potential of the battery, whichever battery we have connected. So we found that potential is directly proportional to the current. Whereas when we remove this proportionality, we get a constant which is supposed to be known as a proportionality constant, and this proportionality constant is also known as resistance. This must be a constant value as resistance is something which is constant for a particular type of matter. So we can say if this conductor is made of iron, it must have some other resistance. If it is made of aluminium, it must have some another resistance. So value of resistance will depend upon which type of matter we are actually using. So all these relation, or you can say this particular law, which is known as Ohm's law, is something which is based upon the observation of Mr. Ohms, who did so many experiments to find out this particular relation or to establish this particular relation. So what he found out is that whatever current is flowing in a wire, it is directly proportional to the potential difference between its ends or across its ends. So we can say if we talk about specifically this conductor, so across, or you can say at the end of the conductor, like across this point. So the potential difference across these 2 points is something which is directly proportional to whatever current is flowing in the circuit. So remember this thing. This should be potential difference between the 2 points. And these 2 points are supposed to be connected with higher potential or lower potential, you can say. So from here, we can say current is something which is equals to V by R. And we can use this particular relation as well to find out different quantities in different circuits. Now, what we have to understand here is we have to understand more about this resistance. So how can we define this resistance? That is the question. So resistance is basically a property of a conductor which opposes the flow of current, which opposes the flow of current. This opposition, which is created or offered by a particular type of matter or a conductor, is specific for a particular type of resistance. So when we try to study a little in a little detail about resistance by assuming that we have a conductor, this conductor has some length L and this conductor must have some area as well. So we found that whatever resistance this conductor offer, it is directly proportional to the length and it is somewhat inversely proportional to the area. So the value of resistance is something which depends upon these two factors, and we can relate these two factors in that way, that it is directly proportional to length as well as it is inversely proportional to the area of cross section of this particular conductor. When we combine these two relations, we got that resistance is something which is directly proportional to L over A. When we remove this proportionality, we got another constant which is supposed to be called resistivity, or we can call it proportionality constant, and this proportionality constant is also known as resistivity. This resistivity is the actual thing which remains constant for a particular type of material. This is something which remains constant for a particular type of matter. Like for example, different materials have different value of resistivity. What we can understand here is that these values are something which depends upon the type of matter. Like for example, suppose if we have silver. Silver has a resistivity value of about 1.59 times 10 to the power minus 8. Similarly, if we talk about some different element like iron, iron has resistivity of about 9.71 times 10 to the power minus 8. As you can see, silver and iron are the good conductors as they can conduct electricity quite easily. So the value of their resistivity is like very small. As you can see, the power, it is 10 to the power minus 8. So it shows that the values are very small. Whereas if we talk about some insulators, like let me assume glass here. So glass has resistivity value of the order 10 to the power 9 to 10 to the power 12. Now here you can see the difference between an insulator and between a conductor. So this value is basically responsible for defining the resistance of any particular type of matter we have. This is what we need to understand here. One more thing that we have already focused on is that whenever a current flows, what we observe some heat, we observe some dissipation of energy in the form of heat. Also, when something gets heated up, or you can say when the temperature of something rises, it starts to expand. And when it starts to expand, its length may increase. And because of increase in its length, we can say the resistance of that particular conductor is going to get changed. So this is the very important point. As length increases, we can say resistance must change. And how can we calculate that change? That should be our concern. So we're going to understand that how to calculate that change. Let's talk about it in a little detail. So here, I'm assuming that this was supposed to be my wire, or you can say a conductor. And this was the initial state of conductor. Now I just connected it with a battery, connected it to a battery. Once I connect it to a battery, what happens here is the temperature of the resistance will start changing. So I can assume that its initial temperature is something which is Ti, or you can also write it as T naught. This was the initial temperature of the conductor. Now what happens here is as this conductor is started getting heat, its length will change. So what we can assume here that initially the conductor must possess some length L. So finally it must have some length L plus L naught, you can say. This L naught represents the change in its length. And this change in length is occurred due to what? Due to change in temperature. And why there is change in temperature? Because when current flows through a conductor, some amount of energy is being lost in the form of heat. And that heat rises the temperature of the conductor. So this is something which we studied in the previous grades, to be honest and to be precise. And this thing says that whatever change in length is observed due to change in temperature, it is somewhat which is directly, or you can say which is equals to initial value times alpha times delta T. Now this was the relation which we studied in thermal expansion, or you can see in thermal properties of matter. So this relation which we studied in thermal properties of matter, we are going to apply it directly here. Now what this relation says exactly? It says that whatever change in length is being produced due to change in temperature, it is equals to initial length times alpha. Now what is this alpha? Alpha is known as coefficient of linear expansion. Why linear expansion? Because here we are going to assume that the change in length is going to be observed. We are not going to observe much change in area. So now just observe the relations here. So delta L, that is change in length, is equals to initial length times alpha times delta T. Now what is this change in length representing? It must be representing L final minus L initial, which I wrote it as L. This must be equals to L alpha delta T. Now L final is going to be L plus L alpha. Now what is delta T? Delta T is T minus T naught. Final minus initial temperature. So if we substitute, if I solve this equation little well, we got 1 plus alpha delta T, or I can write it as T minus T naught. Now this is called the final length. What we are going to do here? We are going to divide the whole equation by radius. Dividing, or you can say we are going to divide the whole equation by area. Dividing both sides by area of the conductor. So what we are going to get? We are going to get LF over A must be equals to L over A 1 plus alpha T minus T naught, like this. Again, we are going to do the same thing. We are going to multiply the same thing by one such factor called resistivity. So what we have to understand here? We have to understand here that resistivity is something which can be calculated while calculating resistance. So as the things are going to change, and keeping this particular relation in mind, we can say that this whole thing is replaced by rho, and this should be equals to rho naught 1 plus alpha T minus T naught. Now this is an important relation. If we understand that how we got this relation, it's fine. If we don't understand that how it got, what's important is to memorize this relation. This relation actually help us to understand that how resistivity is a function of temperature. As the temperature changes, resistivity changes. So the conclusion from this particular section, we can write that for any given material, the resistivity increases with temperature. So resistivity is going to increase if we increase the temperature. Also, for some other materials like semiconductors, which are supposed to be known as some complex materials, they may have resistivity which decreases with time. So this is an exception, and that is something which can also be asked. So we need to keep that in mind as well. So we can say also semiconductors may have resistivity decrease with increase in temperature. So another point that you need to keep in your mind. Apart from this, there is one more thing that we need to understand about carbon resistors, color coding of carbon resistors. But I guess that is something we should just keep aside as of now. If there are any questions from that particular section, just let me know. We'll discuss it accordingly. Did all these things make sense? Whatever we have studied so far?
Yeah.
Now, let's talk about this relation a little more and do some problems based upon this. So, from Ohm's law, we know V is equals to IR. I can write R as V by I. So, what we can conclude from this particular relation? We can conclude from this relation that slope of VI curve is going to give us resistance. Like, what does it mean? So, suppose we have a graph, and this graph represents potential over current. So, whatever slope this graph might possess, like for example, suppose the graph goes like that, and if you have to find out the slope, we have to find out the angle. So, this slope is nothing but it is equals to resistance. So, you need to remember this part as well. It somewhat like came from the question point of view that you have to find out resistance from a given graph. So in that case, you have to find out the slope. And always remember, slope is nothing but rise over run, like how much it moved up and how much it moved in the forward direction. So this is the way to find out slope. Now let's move towards few problems. And if any problem you have to discuss from your side, just let me know. Otherwise, let's solve these some problems. And we also talk about the combination of resistance in this class only. So the question one is pretty simple. I'm taking it like a very easy one. Just think and answer about this particular problem. So the question says that there is a resistance of 10 ohms and we have connected this resistance with a battery of 20 volts. Find current flowing in the circuit. So it's a pretty easy question. Just tell me what should be the answer.
2.
Exactly. So using Ohm's law, we can write V is nothing but product of I and R, and resistance is going to be V by I. As potential is 20, and we have to find out the resistance. So we can say I is going to be V by R. R is 10, so it is going to be 2 amperes. That is absolutely fine. Let's move to the next question. Again, it is going to be a simple one. So the question says that there are two resistors now connected in series combination just like that, and these two resistors have resistance of 10 ohm and 15 ohms, and the battery which is connected here is supposed to be 5 volt. Question is again find current. What should be the current flowing through this particular circuit? So how we are supposed to find it out? Think about it and tell me. So in order to find out what should be the total current flowing through the circuit, we need to understand again this one particular
1 2
relation.
1 2 amperes.
0.2 amperes.
Yeah.
All right, that's correct answer. But let us go through the concept once again. So here, what I was telling is that this particular relation V is equals to IR. This explains so many things. So we need to keep these points in mind. First of all, this V. This is going to be the net potential difference of the circuit. Net potential difference of the circuit means if there are more than one battery connected in this particular circuit, so we have to find out the net potential difference. We'll see some parts about it. Then this is going to be the current. Always remember, current is constant in a circuit where all the elements are connected in series. So here, this particular set of combination is supposed to be called a series combination. So here, the current is supposed to be constant. Similarly, resistance. This resistance is supposed to be the net resistance of the circuit, and we have to find out the net resistance in order to find out current from any of the given circuits. So before actually moving ahead, let us talk about combination of resistance, that how resistance is being calculated in different combinations. So as you have already studied in previous classes as well, resistance can be combined in two ways. The one is supposed to be series combination and another is supposed to be parallel combination. We need to understand these combinations pretty well in such a way that what exactly is going on and what are the characteristics or what are the difference between these two combinations. So see, in series combination, the components which are connected in circuit must be connected like that. Like for example, the initial point and the end point must be same for the two components. Like this B point is the final point or the end point for the resistance R1, whereas for resistance R2, this B point is supposed to be the initial point. Whereas in parallel combination, initial and final points are supposed to be same for different components connected in a circuit. Like for example, if we have this particular way in which the components are connected, so we can say, suppose this is my one resistance, this is my another resistance. Apart from this, this is my another resistance. So in all three resistances, what you'll observe is that the common point, initial and the final point, is supposed to be common. Whereas in series combination, it is not so. So what we can conclude from these two particular diagrams, like if there is a current coming from point A, so this current must pass through the same point B as well. So resistance will going to experience same current when it comes to series combination. That is the first conclusion we can draw from this. So very important point, current remains same for both the components. So that is the very important point. In series combination, always remember current is going to remain same. But here, suppose if current is coming from this particular point. So here current has three particular or it has the possible ways. So I can assume that current must pass differently from different arms. But whatever current is coming from this particular point A, it must be equals to the sum of all the currents which are going to get divided. Because ultimately, when current come to the point B, it is going to add up and make again I. So here what we can say, current divides. A very important relation you need to keep in mind. Here the current divides. Now let's just move to the circuit and find out what should be the value of resistance in each case. So I'm considering that there are two resistors connected in series and these two resistors are connected to a battery of some potential V. I'm marking it as R1, it is R2. Similarly, in this parallel combination case, the resistors are connected this way and these resistors are connected this way and connected with an external battery. So here what we are going to observe, R1, R2 must have some values, whereas this is going to be the potential, but the value of current is going to be different in both the cases. Here if I assume it should be I for both the resistors, but here I can say it is not going to be I. It should be some different value. I can say I1 or I2. So how can we solve this particular problem? And how can we find out the resistance, the right resistance in both the cases? Another point which you can make out from here, if current is not going to if current is not going to get divided in series combination, so there must be something, and that something is called potential. What happens here is potential is something which divides. So V that is this value, must be equals to the sum of both the potential across R1 and R2. Whereas if we talk about this particular case, I is something which divides, which is equals to I1 plus I2. So these are the two equations that we obtain from both the combinations. We just have to solve these equations to find out the value of net resistance in each case. Let's solve these equations and try to memorize each and everything very well. So V is equals to V1 plus V2 in series combination, whereas I is equals to I1 plus I2 in parallel combination. So here, in place of V, what we can write? We'll use Ohm's law once again. So we can say using Ohm's law, V is equals to IR. So here I can write IR net must be equals to IR1 plus IR2. Now that should be the question should come to your mind. Why we take I common? Because I is something which is same for both the resistance. Current is not changing when it passes from one resistance to another resistance. Whereas potential is different. So that's why we just substituted the values. So here we can say the net resistance in series combination is equals to R1 plus R2. That is the very simple way to calculate net resistance in series combination. Whereas if we use same Ohm's law in parallel combination, so we can say I must be equals to potential over resistance. If I is equals to potential over resistance, so we can say V over R net must be equals to V over R1 plus V over R2. Now here I have kept potential as constant because in parallel combination current divides but potential remains same. Potential across R1 and potential across R2 will remain same. That is the external value V. That is what we need to keep in mind. This is a very important conclusion from the parallel combination as well. So make sure that you remember it. So here if we solve the net value in parallel combination, it is supposed to be 1 upon R is equals to 1 upon R1 plus 1 upon R2. So that is how you should keep this value in mind. Again, let me just summarize. Current divides in parallel combination, whereas potential remains same. Whereas potential remains same. Similarly, if we talk about in series combination, so current remains same, whereas potential divide. Now, let's just move back to that problem. So here we were finding out that what should be the current. So in order to find out net what should be the current, we have to find out the net value of resistance. And as you can see that this is a series combination, the net value of resistance must be calculated by simply adding them. So we got 25 Newton. So we got the value of resistance as 25 Newton. Current is supposed to be V by R. V is supposed to be 5 volts and we have here 25. So it is going to be 1 by 5, which is supposed to be 0.2 amperes, which you found already, and that is completely correct. But the understanding concept is more important. Now I'm giving you a little tough problem. Try to solve that out, keeping all these points which we have discussed so far, and let me know whether you are able to solve it or not. So, question is getting a little tricky now. There are two resistances connected to an external battery of potential 100 volts. The value of these two resistances are 20 ohm and 40 ohms. You have to find out current passing through 20 ohm resistor. Think about it and tell me that what should be the value of current passing through 20 ohms resistor. Again, it's a very simple one. You just have to keep all the points in mind which we have discussed so far. If you are able to keep those points in mind, you'll be able to solve it. Try it out and tell me. Are you there?
Yes, sir. I'm solving it.
Okay, go ahead.
1.6 amperes.
How did you got it? Tell me.
Add both of the resistance together and divide it by voltage.
No, no, no. This is not how you're supposed to do it. Think again.
Okay. Mommy.
What happened? Is everything all right?
Yeah, there was a small earthquake. I got scared. Sorry.
Seriously?
Yeah.
Earthquake.
Yeah.
Okay. All right. Let's try to understand that how we can solve it. First of all, if we have to find out current specifically passing through 20 ohm resistance, so we can mark it as I1. This is what we have to find. This was the question. So how we are supposed to solve this? So in order to solve this value of current, we first of all have to understand that there should be some value of net current that must be coming out from the battery. So first of all, we have to find this value of current, then only we'll be able to find out the value of I1, or you can say the current passing through 20 ohm resistance. Now, what are the conditions for the parallel combination? The conditions for parallel combinations is that the potential is something which remains constant for both the components. So potential across 20 ohm must be equals to potential across 40 ohms, which is supposed to be 100 volts. So that is one point we need to keep in mind. Now, in order to find out the net current, we need to use Ohm's law. And Ohm's law says that V is I net times R net. So how can we find out the net resistance here? So net resistance can be find out using the parallel combination relation. So we know that 1 upon R net is equals to 1 upon R1 plus 1 upon R2. When we solve this, we'll have a certain value. Let's figure it out what it is. So it is going to be, I can say 20 and 40 and take LCM. We're supposed to get this. So R is going to be 40 over 3. This is the net value of resistance. As we got the net value of resistance, we can find out the net value of current as well using this particular relation only. So here we can find that I must be equals to V over R. Potential is 100 where R is supposed to be 40 over 3. So it is coming out to be 2.5 times 3, which is 7.5 amperes. The total value of current that is going from the battery is supposed to be 7.5 amperes. So as the total value of current is 7.5 amperes, we need to find out the value of current which is passing through this 20 ohm resistance. Again, we'll apply the same Ohm's law. We have the current, we have the potential, we can find out the value. So how can we do so? Again, we'll use Ohm's law here. So Ohm's law says V is equals to IR. Potential across this resistance is 100. Current is supposed to be, we can mark as I1, where R is supposed to be for 20 ohms. So I1 is going to be 100 over 20, which is supposed to be 5 amperes. That is what we need to keep in our mind. Similarly, we have to find out I2 passing through this particular resistance, it is going to be same relation we'll use. I2 is going to be 100 over 40, which is supposed to be 72.5 amperes. Once you add upon these values, so I must be equals to I1 plus I2, and it should be same as that of total value of current, which is 7.5. And if it is same, we can say our solution is correct, or whatever we have found is completely correct. So this is how you are supposed to relate or solve all these particular problems. Did you understand this part?
Yes, sir.
All right, so let's move to another question. Try that question out. It is again the same one. I want you to try it out. The question says that again there is a combination of two resistances connected in series in such a way the battery with which it is connected it is of 30 volts. The resistance is supposed to be of 2 amperes and 8 amperes. The question is find potential difference across 2 ampere, sorry, 2 ohm resistor. It should be ohms. So try it out. Tell me the value of potential difference across 2 ohm resistance. Think about it and tell me.
2.7, 2.7 ampere.
You have to find potential difference,
Okay.
not the current.
Okay.
So in series combination, potential must be different for both the cases, for both the resistances.
Yeah.
So as the potential difference is going to be different for both the resistances, we can say potential difference is going to be I times R1. Now what is this I? This I is going to be the total current coming out of the battery. As this is a series combination, so current must be same for both the resistance. How can we find out the total current? Again, we'll use the Ohm's law. So I must be equals to V by R, where it is supposed to be V net or V total by R net, as this is a combination. So V net is 30, where R net is going to be 2 plus 8. As it is a series combination, we will simply add it. So the total current we're going to have with us is 3 amperes. As we got the value of total current, we can substitute here in this particular relation and multiply the value with R1. We get the value of potential across 2 ohm resistors, which is supposed to be 3 times 2, that is 6 volts. Similarly, we have to find the potential across the 8 ohm resistance. It is going to be 3 times 8, which is supposed to be 24 volts. Always remember, in series combination, the sum of potential should be same. So V1 plus V2 must be equals to the net potential of the battery, which is 30. And as we can verify it, we are getting it as 30 only. So whatever we have solved is correct. This is the way to verify your answers as well. So this is a particular way to solve all these problems, and make sure you remember the process. And if you remember the process, you'll be able to solve so many questions from this particular section. Now just tell me any question you want me to discuss, which you discussed or started in class, but you didn't manage to get it. Tell me about any problem. If you have any problem,
Okay.
just share it.
Okay. Um, Okay, I sent you the page I was having trouble in. It was, I think, 30, 33, and 27.
Okay. So first of all, let us see the 27th problem. So the 27th problem says a copper wire has 25 milliohm resistance. So copper wire has a resistance of 25 milliohms. Now remember this 25 milliohms supposed to be written as 25 times 10 to the power minus 3 ohm. Every time we are solving any physics problem, we have to make sure that we solve the physical quantities in SI units. So milliohm is not an SI unit, so we have to convert it into ohms. Now this value of resistance is supposed to be at temperature 20 degrees Celsius as per the question. When the wire is carrying a current, heat produced by the current causes the temperature of the wire to increase by 27 degrees Celsius. Now the question is, as the current passes through it, its temperature increases by 27 degrees Celsius. So the final temperature must be initial temperature plus 27 degrees Celsius, which is supposed to be 47 degrees Celsius in total. So the first thing is, what is the change in wire's resistance? We have to find out the wire's resistance. So we already understood that how we can find out the final resistance of the wire. So the final resistance of the wire must be equal to initial resistance 1 plus alpha delta T. So in order to solve this equation, we need to know the alpha. Alpha for which wire? Copper wire. So do you know what is the alpha for copper wire? Any idea?
Alpha for copper wire is
See, the PDF which you have shared, it has the value of alpha for,
1.68 times 10 to the negative 8. It's in the textbook.
yeah, but that is the value of resistivity which I was saying, whereas the alpha for copper wire is supposed to be 0.0068. That is the value of alpha for copper wire. It is already given in your textbook, you can check it out.
Okay.
Yeah. So we got the value of alpha, we have initial value of resistance, we have to find out the final value of resistance, we have to understand what is the change. Change in temperature is supposed to be 27 degrees Celsius. So we'll substitute all the values and we can find out the value of final resistance at 47 degrees Celsius. So therefore, final resistance must be equals to the initial value of resistance, which is 25 times 10 to the power minus 3, 1 plus alpha, which is 0.0068 times 27. Just solve this particular relation and tell me what is the value of it. So 27 times 0.0068 plus 1 multiplied by 25. It is going to be 29.59 times 10 to the power minus 3. So final resistance must be 29.59 milli ohms. This is what we have to find and this is what we got. So you can see here by changing the temperature by 27 degrees Celsius, we increase the value of resistance by 4.59 milliohms. And that is what we have to find out in the very first part of this particular problem.
Okay.
Again, there is another part which says if its original current was 10 milliamperes, what is its final current? So the question says if at this particular temperature current is supposed to be 10 milliamperes, so after increasing the temperature 27 degree plus 27 degrees Celsius, what is the value of current here? So that's pretty simple. Remember this particular relation only. We'll apply the Ohm's law in this particular relation once again. As Ohm's law says V is equals to IR, so R must be potential over current. So if we substitute this value, we can have potential over I final must be equals to potential over I initial 1 plus alpha delta T. Potential will remain constant as we're not going to change the battery, but yeah, current will change as temperature has increased. So the value of final current must be equals to 1 over. Now, what is the value of initial current? It says 10 milliamperes. So it is going to be 10 into 10 to the power minus 3, 1 plus alpha. Alpha is 0.0068 times. Change in temperature is 27 degrees Celsius. We'll put it this way only. So once we'll solve this equation, we'll have the value of final current. So it is coming out to be, so 0.0068 into 27 plus 1 is going to be 1.118, 1.1836 over 10 to the power minus 2. So if you try to solve this particular value, we'll get I final, or you can say the current at 27 degrees Celsius increasing temperature must be equals to, if you solve this equation, you'll get the value. So it is supposed to be 0.01 divided by 1.1836, which is supposed to be 0.00844, or you can say it is going to be 8.44 milliamperes. So you can see here, initially at 20 degrees Celsius, the current was supposed to be 10 milliamperes that this battery is discharging. But as soon as we increase the temperature by 27 degrees Celsius, the value of current which is being discharged, it is reduced. So you can see the effect of current, the effect of temperature change in current as well as in resistance. In case of resistance, as temperature increases, resistance increases. But in case of current, as temperature increases, current decreases. That is the very important thing that you should keep in mind. Did you understand this particular part?
Yes, sir.
Also, just remember the relation. Relation is very much important. Again, let's move to the next question, which is at 33rd, right? So the 33rd question says, at 20 degrees Celsius, a silicon rod of uniform cross section is connected to a battery with a terminal voltage of 6 volts and 0.5 amperes current results. The temperature of the rod is then increased to 25 degrees Celsius. So we have given the initial temperature. I can mark it as T naught, which is supposed to be 20 degrees Celsius. We have a silicon rod. So we need to remember the name of the material with which the rod is made. It is made up of silicon. It has some uniform area and it is connected to a battery of 6 volts potential difference. So when we just connect the 6-volt battery, we get a current of 0.5 amperes here. The question says that we increase the temperature to 25 degrees Celsius now. So the first part, what is the new resistance? We have to find out the new resistance. In order to find out the new resistance, we have to first of all understand that what is the value of initial resistance. So using these two values, we can find out the initial resistance. So V is equals to IR according to Ohm's law. So R is going to be V by I. V is 6, I is zero point 0.5. So resistance initially is going to be 12 amperes. So we got to know the initial resistance is supposed to be 12 amperes. Now we have to find out the final resistance. So again, we'll use the same relation. R final must be equals to R initial 1 plus alpha delta T. Now think about the value of resistance, or you can say the value of alpha for silicon wire or a silicon conductor. So in order to have the value, again, you can use the table which is given in the book only. So the temperature coefficient or the value of alpha for the silicon wire is supposed to be negative 0.07 per degree Celsius. So negative means as the temperature increases, the resistance is going to decrease. So this is a special case. That's why this value is negative. This is a special material. That is also you can understand here. So once we substitute the values now, we get the value of the final resistance. So R final must be equals to 12 times 1 plus alpha, that is negative 0.07 times delta T. What is delta T? What is change in temperature? What can I say about change in temperature? We can say the change in temperature must be equals to 25 minus 20, which is 5 degrees Celsius. So we can simply substitute 5 here. Once we'll solve this relation, we'll get the value of final resistance. Remember, as the value is negative, so that is the reason we are going to get the final resistance lesser than the initial value of resistance, or you can say less than 12. So it is going to be 0.07 times 5, which is 0.35. We just subtracted it from 1, we get 0.65, and if we multiply it by 12, we'll get 7.8. So the value of resistance has drastically changed or decreased to 12 to 7.8 ohms. And this is all because of the negative value of alpha that silicon possess. So that was the first part we have to do in this particular question. And I hope you understand that how all these things went. Similarly, if we try to solve the next part, so the question says, how much current does it carry? So if the final value of resistance changes, what will be the effect on the current? Obviously, current will change. Again, by using Ohm's law, we can say V is equals to IR. So IR is equals to V by R. Potential will remain same as we are not going to change the battery. So 6 over 7.8. So 6 over 7.8 will result in increase in value of current. Initially, the current was 0.5 amperes, but now the value of current will definitely change and it is going to increase, and it will increase to the value of 0.76 amperes. You just have to solve, or you just have to apply the basic formulas or basic rules to find out that how all these things are going to change. So this was the first part. This was the second part of this particular problem. Now, another part is there in which it says, if you wanted to cut the current from its room temperature value of 0.5 ampere to 0.4 amperes, at what temperature would the rod have to be? Now, this is the trickiest part. The question says the initial value of resistance, or initial value of resistance of 12 amperes, 12 ohms, gives us the current of 0.5 amperes. And the temperature is supposed to be what? 20 degrees Celsius initially. Now the question says you have to cut the value of current to 0.4 amperes. In order to cut the value of current to 0.4 amperes, what should be the final temperature? That is what it is asking. So in order to understand this particular fact that what should be the final temperature, we have to utilize that relation which we are using from past few times. So here resistance must be equals to R1 plus alpha delta T. You have to keep it in mind. So in place of resistance, we can put V by I. So V by I final must be equals to V by I initial 1 plus alpha delta T. So from this equation, we have to find out the value of delta T. Once we have the value of delta T, we can find out the value of final time or temperature. So V will cancel out V. What is the final value of current? It is expecting us to have 0.4 ampere. What is the initial value of current? We were having 0.5 amperes. 1 plus alpha. Alpha is supposed to be what? Negative of 0.07 multiplied by delta T, and this is what we have to solve here. So if we solve the equation, we'll get the value of delta T. Let's try to solve this equation. So 0.5 over 0.4 minus 1 is equals to negative of 0.07 times delta T. Once we solve this equation, we'll get 0.1 over 0.4 must be equals to negative of 0.07 times delta T. When we solve this equation, delta T must be equals to 1 by 4 times 0.07, that too in negative. So it is going to be 1 over 0.28, that too in negative. So here we got the value of delta T. So initial delta t can be written as T final minus T initial, which is equals to negative 0.28. So what is the value of T initial? It is 20 degrees. So 20 minus this. If we do this, we'll have the value of final temperature. So you can simply solve this particular relation to have the value of final temperature, which is going to be around 20 times 0.28 minus 1 over 0.28, which is supposed to be 16.42 degrees Celsius. This is the value of final temperature at what we have to keep it in order to have the current 0.4 amperes. Remember, initially the temperature is 20 degrees Celsius. To have the current of 0.4 ampere magnitude, we need to increase the final temperature, or you can say we actually have to decrease the temperature to 16.42 degrees Celsius in order to have 0.4 amperes of current. Does all these things make sense?
Yes, sir.
Did you understand the complete process, like how we are supposed to substitute the values,
Yeah.
get the results and all? All right then. So just make sure that you practice all those parts, uh, whichever is there in the book. Try to solve as many questions as possible. And if you came across or if you're having any doubt, just let me know. Yeah, it's better to
Okay.
do as many questions as you can because that is the main thing.
Okay, sir.
All right. Let's keep it till here only.